Hello everyone, my name is Pedram and I'm a professor in data analytics. Welcome to another episode of Deep Learning. Alright, this is the last part of Module 3. So in this module, we are looking into machine learning fundamental concepts. So in part 1, we covered some basic concepts. In part 2, we talked about the boosting algorithms. We reviewed XGBoost, CatBoost, and LightGBM. And we also provided how to do these models using PyCaret in Python. In this part, we're going to talk about some challenges that we might face when you're dealing with time series dataset. So without further ado, let's jump into it. So Module 3, Part 3, Challenges in Time Series Machine Learning. When it comes to the time series machine learning, there are some challenges that you might face down the road and which are not necessarily widely or commonly covered in textbooks or courses out there. So these challenges are the ones that if you're doing time series analysis, you should be very aware, and it might make a big difference in terms of model performance. So in a nutshell, I'm going to highlight the most important ones that at least I think these are the most important ones, but the challenges for time series is not limited to these ones that I listed here. So the first one is non-stationarity, right? So we know that many time series data exhibit non-stationary behavior. This means that the statistical properties like the mean and variance of the data changes over time. So this can make it difficult to model the data and make accurate predictions. So we have to take into account this concept of non-stationarity, because if the data set is non-stationary, not necessarily all the extrapolations are valid, right? So we know that extrapolating into the future may not necessarily be valid if the data set is basically non-stationary. The second one is seasonality, right? So we know that time series, quite often shows the regular patterns, and these patterns can be daily, weekly, or in terms of, for example, stock market, it can be hourly, by minutes, and or yearly seasonality, right? So these patterns sometimes can be difficult and tricky to model and can lead to errors in predictions if we don't take into account these kind of seasonality. So we should be aware of those things as well. The next one is, well, this is also limited to any kind of data set, but it's more emphasized in time series data set, and that's the amount of data available. Let's call it limited data, right? So time series data are often collected over a limited time period, which can make it difficult to train a model with sufficient amount of data. And probably this is one of the reasons that even as of today, the state-of-the-art neural networks architectures like transformers, they cannot easily outbid some even simple econometric time series models or boosting algorithms when it comes to handling structured time series, right? So maybe one of the main reasons is that the time series data is kind of limited. It's unlike the other type of data set that we have. And then finally, and I think that maybe this is the most important one, is basically your time series, as the name suggests, the data is time dependent, right? So this time dependency is basically it means that the next value of your observation depends on the previous value, right? And this characteristic makes the problem harder to solve than regular and other regular supervised learning models, right? And this means that when you're doing cross-validations, right? So if you're doing, for example, K-fold cross-validation, within each fold, you cannot simply shuffle the data. Or when you're using bootstrap, you cannot simply shuffle the data because simply the time series are not IID. So there are different ways and techniques that we should use when it comes to cross-validation, when it comes to bootstrapping, and we have to apply these methods when we are ensembling, for example, decision trees, right? So in the previous part, when we talked about boosted algorithm, we said that, okay, at the end of the day, we are ensembling a bunch of trees, we are bootstrapping over them, and we look at the performance of the model by looking at the cross-validation performance, right? So when it comes to the concepts, we have to be very careful that for time series, cross-validation is different. We have to do it differently simply because the data is not IID. The bootstrapping is also different. So let's take a look into these concepts in more detail, starting with stationarity. Okay, so for those who might not be quite familiar with the concept of stationarity and what makes a data stationary, maybe this visualization help. It's a quite simple concept. In a stationary time series, we say that the statistical properties do not depend on time, right? So what do we mean? So look at an example where the data shows a stationarity. So this is a stationary data. And as you can see, it seems that the average, let's say the average is sitting around here, over time is kind of constant. The variance is kind of constant, and the autocorrelation or covariance between each 2 points in time, at least visually here, seems to be constant. If you want to see how it looks for non-stationary data, basically, if there's a trend and seasonality in the data, that data set is not going to be stationary. Why? Because, for example, in this data set, we see trends, right? We see trend and seasonality. And if you look at the average in any, let's say, for any window period in time, so here maybe this is the average, and the average is increasing, right? So as you can see, this average is not constant over time. And in the other example, so in this plot, as you can see, the variance is not constant over time. Maybe average is constant, but the problem is that the variance is changing when I go from time to time. If I look at the period of, let's say, 10 period uh, frequency, right? And then finally, in this example, as you can see, maybe the average is constant, maybe the variance is constant, but the covariance or autocorrelation is not constant. It simply means that the relationship between current value and the past value might be different at different points in time. So maybe I'm looking at the autocorrelation between these 2 points. And if I want to look at the same window, so maybe these 2 points and then these 2 points, the autocorrelation, as you can see, it's changing, right? So basically, if average, variance, and correlation or autocorrelation is changing over time, that data set is non-stationary. And what's the well, I don't want to call it problem. What's the issue with non-stationary data and makes it more difficult to predict, especially for example for a stock market, right? The reason is that at any point, so for example, let's look at this data set. Let's look at this one. And imagine, regardless of what model you use, machine learning, deep learning, you name it, you have a train set, validation set, test set, right? And in time series, your train set can be something like this. And then we're going to talk about cross-validation in the future slides, but whatever it is, it's going to be something, let's say, in this range, right? Or even in the full range of the data. But when it comes to predicting futures, right? So in the futures, the data is taking some values that the model has not seen those values for observations in the entire training, validation, or even cross-validation process, right? So that's what makes it a little challenging when it comes to the forecasting non-stationary data set, right? So for example, when it comes to stock market, we know that it's not stationary necessarily, and it's difficult, or if not impossible, to make stock market price predictions. There are some hopes when it comes to stock market return predictions, simply because returns are stationary and it's easier to model those kind of time series. Okay, so what are cross-validation techniques in time series? Remember, with time series, especially if it is a stationary, we simply cannot shuffle the data because time series are autocorrelated and they are not IID, right? Even if the data is stationary, there's still some time dependencies, like in ARIMA models, right? After all, it's not quite a white noise, so we need to use different cross-validation methods, right? And so basically the main reason is that we cannot shuffle the data, and even if you can shuffle the data, there's still some time dependencies. And we need to make sure that we have to avoid data leakage, right? So we're going to talk about data leakage in the next slide, but in a nutshell, data leakage happens when the training sets and test sets are sharing some information, right? So imagine this is our K-fold cross-validation. We need to make sure that there is no data leakage between train set and test set, right? In these points. So there are ways to fix that when it comes to time series, right? So based on these requirements, we're going to deal with different cross-validation methods for time series, but the three most commonly used ones, or the ones that work in practice, are these ones, right? The first one is Purged K-fold cross-validation. The second one, which most probably you have seen this before, is walk forward rolling or expanding windows cross-validation. And the third one is combinatorial purge cross-validation, this is actually a quite interesting one, which was developed by Marcus Lopez do Prado, which he talks about this method in his fantastic books, which is called Advances in Financial Machine Learning. Okay, so let's look into the first one. Purged K-fold cross-validation. So the idea of Purged K-fold cross-validation is all about data leakage, right? And as I said earlier, leakage takes place when the training set contains information that also appears in the test set, right? Because this is time series, right? After all, t and t plus 1 are serially correlated. And if you tend to put them in different buckets, then these buckets have some data leakage into each other, right? So this is not surprising at all. And what's the problem of leakage? The problem is that leakage will enhance your model performance. So you're going to get fake model performance, right? So what is the solution? And actually, let me show you this one. So imagine this is your train set, and obviously you have a non-stationary data set here, the time series here. So let's say we have train set, test set, and again, another train set, and we can go ahead and multiply it into multiple train and test splits, right? And as you can see, there is this overlap. What is the solution? The solution is what Marcus Lopez do Prado calls purging and embargoing in his book Advances in Financial Machine Learning, right? So, and the idea is quite simple. So purging is, so if you pay attention to this green shaded areas, so purging happens basically to reduce the data leakage. We are going to remove observations or purge observations from the train set that have overlap with the test set. Remember, this is our, let me use the right marker. This is our train, this is test, this is train again, right? So the idea is that remove these observations that overlap between train and test. So we're going to have cushions. Let me use the right color. Okay, we're going to have an extra cushion here, an extra cushion here, right? So this is the idea of purging. So what is embargoing? And the embargoing is, so we are going to add an extra buffer or extra cushion right after the test set and right before the train set to make sure that these serial correlations are avoided or minimized, right? So this is the idea of purging and embargoing. Now, if we apply this purging and embargoing things to K-fold cross-validation, this technique is called Purged K-fold cross-validation. Basically, by adding purging and embargoing whenever we produce a train test split in our K-fold cross-validation. Let's say I have my own 5-fold cross-validation, right? So 1, 2, 3, 4, 5. And every single time that you see a train test split, you're going to apply purge and embargoing. So for example, here right after test, we're going to have, here we are going to have purge, embargo, and then we are going to have purge, purge, embargo. We're going to have purge, purge, embargo, and etc. Right? And we're going to apply this and then calculate the performance on the test set in each fold. And just like any other K-fold cross-validation, we are going to combine these performances. For example, take the average if it is, let's say, RMSE, and then call it the cross-validation performance metric. All right. The second cross-validation techniques for time series is walk forward, right? We can have two forms of walk forward cross-validation. One is using rolling windows on the right, and the other one is using expanding windows. So starting from the walk forward cross-validation rolling windows or sliding windows, we can say in this method, the data is split into series of overlapping windows, and as you can see, these ones have overlap, right? Where each window represents a train set and the following window represents the corresponding test set, right? So we have our train set and the following one is going to be our test set. So the size of the test set is fixed. The size of the rolling window, it can be fixed. It can be different, right? So these sizes can change. Well, we are going to use this sliding walk forward cross validation when the data set, when we have a large number of observations, right? When we have large number of observations and to avoid structural changes over time series, we would be using rolling windows, right? Because, especially when it comes to stock market, Apple 10 years ago is different from Apple today, right? So it's not useful to use, by useful, it's not quite practical to use information from 10 years ago necessarily when you want to study what's the behavior of Apple stock price today, right? So maybe you should use rolling windows of 1 year or 6 months, right? So that's the idea of walk forward rolling windows cross validation. And for expanding, that's basically similar to sliding window, but the training set is expanded with each iteration, right? So as you can see, this is your train set first, and we're going to expand it, and etc. And we keep the size of the test sets similar. So this method is used when you have limited time series available, right? So if you have a small data sets, there is no structural change in the time series, you can apply walk forward. But regardless if you use rolling or expanding, there are some advantages and disadvantages for this cross-validation technique. So let's talk about the advantages. So maybe the biggest advantage of walk forward cross-validation is it has a clear historical interpretation, right? Basically, especially if you're doing backtesting, it is consistent with the historical backtesting and paper trading, right? So you see, for example, in expanding window, you see from day 1 to day t, and you observe one full path of the data, and this is basically your historical data, right? And so we can say that history is acting some sort of like a filtration, and the test set is completely out of sample, right? So here at each fold, at each cross-validation fold, we're seeing test set is completely separate from the train. And because test set is always coming after the train set, we don't need to do any kind of embargoing, but we need to do some purging, right? So we need to do some purging to make sure that there is no data leakage, okay? So these are the advantages. What is the disadvantage? So the disadvantage, and again, maybe the biggest one, is that it's what's called a single scenario test. It's basically show you the historical path. It's going to generate one path from day 1 to day t. And usually this is your historical data, and when it comes to trading, the model can overfit. The model can overfit if there's only one path, right? So the solution is what we call combinatorial cross-validation. That's basically the idea of combinatorial cross-validation, is to generate multiple of these paths that makes your performance metrics more robust, with a smaller variance, right? So that's the first disadvantage. The second disadvantage, which only applies to the expanding window, is basically the initial decisions are made on a smaller proportion of the data, right? So for example, here, whatever we are doing in the first fold, the decision is based on this train set, then next one, then next one. And as you can see, the initial decisions are based on a fewer observations. So we don't have this problem with the rolling window, but the problem with the rolling window is that these the folds are not necessarily large, right? So again, this is advantages and disadvantages of walk forward cross-validation, but this is one of those cross-validation techniques that it's most widely used, and it works. If time series is stationary, and this technique works just fine. And this is the one that comes with many Python packages like PyCaret, like scikit-learn, and etc. All right, the last one is called CPCV, Combinatorial Purge Cross-Validation. Okay, so this one is quite unique, especially when it comes to backtesting trading strategies, and it's very helpful because it gives us multiple backtest paths that span the entire data set. So what do I mean by that? So let me emphasize it one more time. The goal in CPCV is to generate multiple unique backtest paths that span the entire data set. Remember, in purge cross-validation or in walk forward cross-validation, we went through day 1 to day t, capital letter T, only once. That was basically your historical data. And especially when it comes to backtesting trading strategy, it can overfit. It can simply overfit. But the idea of combinatorial purge cross-validation is we're gonna do something like this. Imagine. Let's look at this one actually. I'm going to tell you what do we mean by S and what are the different things on the vertical axis. We call them group. So imagine you have, I don't know, 700 something observations, right? Let's call it 700 observation. And I'm going to divide it into 6 groups. So let's say group 1, 2, 3, 4, 5, 6. 6 groups that within these groups, we are not supposed to shuffle the data, right? So let's say you can think of these groups as months, right? So groups can be, in this example, months, right? So we don't want to shuffle the data within each month, right? And I have 6 groups here, so my G is equal to 6. And I want to test, so I want to keep 2 months of these 6 months as for my test set, right? For all these 700 observations, right? So let's say I want to test 2 groups or 2 months. So how many different ways can I do that? It's a combination of 2 of 6, right? So 2 of 6 is going to be basically 15 different ways, right? 6 multiplied 5 divided by 2. And so now that this is where these S's are coming from, S1 through S15, right? So these are basically different splitting ways we can have if you have 6 groups that you don't want to shuffle them, and you want to for each cross validation you want to use 2 of them as a test set, right? So we're going to end up with 15 different splitting methods, right? So now out of these 15 different splitting methods, we can come up, in this example, we can come up with 5 unique paths. So basically here, this is, and let's go ahead and label them with numbers. So this is unique path that spans the entire data from, let's say, month 1 to month 6, day 0 to, I don't know, 700, the unit is different, right? So this is path number 1, path number 2, path number 3, number 4, number 5, and etc. Right? So again, there's a formula where we can get this number 5 here, but whatever it is, at the end of the day, using CPCV, now combinatorial purge cross validation, we were able to generate, in this example, 5 unique paths that span the entire data set. So what's quite unique about this approach is that it will help us to avoid overfitting, and basically we don't get super optimistic performance metrics, right? So this is really, really important. So, and remember, in each path that we generated, in this example we had 5, we can look at the model's out of sample performance for the entire time period. So one last thing I wanted to emphasize is that, of course, during this combinatorial purge cross-validation, we are also using purging and embargoing. So this means that whenever we have train and test split, we're going to use purging before and after each training test, and right after the test, we're going embargoing. We're using embargoing. All right, now let's move on to time series bootstrapping. As we discussed earlier, because there is this time dependencies in time series data, note IID bootstrapping simply does not work because we cannot shuffle the data randomly. And so we know that the bootstrapping is random sampling with replacement. So if there's time dependency, we cannot do that. So what do we use for time series bootstrapping methods? There are 2 general types of bootstrapping methods for time series. One is parametric, the other one is non-parametric. Parametric ones are simply based on models, right? So we're going to work with models with IID residuals and resample from those residuals. So let's say, for example, we have an autoregressive model or a REMA model. We feed the data, and then we come up with the residuals. The residuals are going to be IID, and we're going to simulate back from those residuals, right? So we're going to simulate a synthetic time series from those residuals, right? And so this is a parametric approach. The second approach is non-parametric, right? So in non-parametric, we're going to call them block bootstrap, and it is where the data is directly resampled, right? So the underlying assumption is that these blocks can be sampled so that they are approximately IID. Yes, the data set, the time series itself is not IID, but we're going to put them in different blocks, and then we assume that those blocks are IID, right? So depending on how we define those blocks, we can come up with different non-parametric block bootstrap techniques, and we're going to cover 3 of them here. Moving block bootstrap, MBB, circular block bootstrap, CBB, and stationary bootstrap, SB. Okay, so the first one, moving block bootstrap, MBB. MBB samples overlapping fixed size blocks, and the size is M, of M consecutive observations, right? So the idea is that, so imagine this is our observed data, and we are dealing with overlapping fixed size. So this is one block, here's another block, you get the idea, different colors, right? So in this example, we're going to have 5 blocks with fixed size, whatever the size is. Then we're going to put them together, we call it resample blocks, and then we are going to sort them in a way that the the length of the resampled blocks is the same as the length of the observational data, right? This is going to be our bootstrap data. And now we can repeat this process many times. We can generate many bootstrap observations, right? And just pay attention that the blocks indices starts from number 1 to number t minus m plus 1. So what does that mean? Imagine we have on the left hand side we have 9 observations, 1 2 3 4 5 6 7 8 9, right? And imagine our m is equal to 3. The block size, the fixed block size that can be overlapping, is 3, right? So this is block number 1, block number 2, and etc., right? So the index of the block bootstraps is going to start from index number 1. So here this is index number 1, and it goes all the way to index number capital letter T minus m plus 1. So our T is 9, m is 3 plus 1, so this is index 7. This is the start of the last block available in the data, right? So basically index 7, 1 2 3 4 5 6 7. So this is going to be our last block. And as you can see, maybe one thing that you may notice that the very last block is going to be the observations here are going to only be repeated once in this block, right? So maybe we should fix this problem, and this is exactly the motivation for circular block, right? The circular block assumes that the data lives in a circle, and now we can connect the first observation to the very last observation, and we can build more blocks on top of that. Then the very last observations are going to be repeatedly the same amount of time compared to the other part of the data observations. So here's the CBB, circular block bootstrap. As I said, it's a simple extension to the MBB, and which assumes that the data lives in a circle. So this is your T1, and it goes all the way to T capital letter T, last period, and then it goes back to T1 again. So this helps, first of all, it makes sure that your bootstrap has better finite sample properties, because all the data points get sampled with equal probability. Remember, in moving block, let's say, in moving block bootstrap, the very last observations have fewer chance to show up in the data. But if I make it circular, then they're going to be repeated in a few forward blocks, and they have equal chance of showing up in the bootstrap. So this is the caveat of MBB, which is covered by CBB, circular block bootstrap. All right, the last one is a stationary bootstrap. So stationary bootstrap is, again, simply an extension to moving block bootstrap, but here the block size is no longer fixed. So if you remember, in our previous example, our block size was equal to 3. So we had the data, and we came up with blocks of 3 observations. They could overlap, something like this. But now, in stationary bootstrap, we are going to choose an average block size of m. So we're going to say that on average, the block size is 3. So maybe I have a block of 2, and then I have a block of, I don't know, maybe without overlapping 4. And as you can see, the average is going to be 3. So the idea is that we can have different size blocks. And what makes it interesting is that if this stationary bootstrap is applied to stationary data, our resample pseudo time series. Remember, the bootstrap data, this is a synthetic time series, right? This new pseudo time series is going to be stationary. And this is very important, because that's not the case for moving block bootstrap or circular block bootstrap. So in many cases, we transform the time series data to be stationary first. And then now, if you want to apply any kind of bootstrapping, the pseudo time series better be stationary, right? Because you want to, for example, you're applying some ARIMA models. ARIMA works under the assumption that the time series is stationary. And now, if you want to look at the performance of the model in simulated data, your simulated data or synthetic data better be stationary, right? And I think one last thing I want to emphasize, that the popularity of stationary bootstrap is coming from the fact that it is hard to come up with the optimal value for a fixed block size of m, right? This is going to leave your hands, it's going to give you more room to just focus on the average value of that m, and then you can change the size of these blocks. It can be any number, right? And this, by the way, the last property that we talked about, and when a stationary bootstrap is applied to a stationary data set, the synthetic data is going to be stationary. it can be mathematically proved. Actually, there's a paper that covers this. If you're interested, you can look up the proof on the paper. All right, I think that's pretty much it. These are all the topics that I wanted to cover when it comes to time series machine learning and what are the challenges in time series machine learning. This concludes our module number 3 in the deep learning course. So now we are familiar with everything we need to know to move on to module 4, 5, and etc. So in the following modules, we're going to start by the very basic neural network model, and then we're going to extend the idea to more advanced architectures. Okay, so until the next one, take care.